Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called Oil and Gas Industries Enterprise-Wide Optimization. Advanced Analytics Solutions. To provide these services, HI is supported by its business partners, GAMS, IBM and TD SYNNEX, all of which are producers of artificial intelligence technologies. HI is a company at the forefront of high-performance artificial intelligence. Oil Supply Chain Optimization. The oil industry includes global processes of exploration, extraction, refining, transportation and marketing of petroleum products. The largest volume products in the industry are fuels, natural gas, fuel oil, and gasoline. However, petroleum is the raw material for many chemicals, including pharmaceuticals, solvents, fertilizers, pesticides and plastics. The oil and gas supply chain is made up of 4 links: upstream, midstream, downstream and retail. The links are connected by multimodal transport networks. The table, elaborated by IBM, shows a resume of the optimization solutions for oil and gas enterprises. Oil supply chain optimization meets all the software solutions developed by HI, in different areas of application of mathematical optimization models, oriented to planning and to scheduling operations, in different business of the petroleum product supply chain. The table presents a summary of the oil production and the transformation mathematical models developed by HI. The table presents a summary of the oil transport mathematical models developed by HI. Oil Enterprise-Wide Optimization integrates mathematical models for each of the links in the oil supply chain, in such a way to management the planning of the supply chain with a holistic vision. The design of HI Oil AWO was the result of work done for a multi-business oil company. The union of models, and their coordination, forms the hypothalamus of an oil enterprise. Oil and Gas Production Optimization integrates reservoir behavior as part of the optimization model. Considers 4 fundamental aspects: production system, reservoir behavior, operating modes of wells, and flow in the hydraulic system. The objectives of optimization models depend on the planning horizon, and can be divided into real-time, advanced control, scheduling, short-term production optimization, planning, medium-term field optimization, strategic operations planning, long-term planning, reservoir recovering optimization, and strategic investment planning, portfolio optimization in oil exploration and production. Operations planning integrates multiple fields, which in turn comprise multiple oil or gas, which are operated by means of multi-well interconnected. Interconnection, which occurs at the surface facilities, allows gas and oil can be sent to storage for subsequent release through a transport system. The goal of optimization is to determine the contribution of each well, to meet demand while minimizing the total cost of the operation during the planning horizon, which is associated with energy consumption in the production system, more investment in adaptation of deposits when this restructuring of the productive system topology is allowed in the model. The model includes the following entities: production system, field, oil field, well, collector, platform, separator unit, and tank. For the modeling of the hydraulic system, reservoir plus surface facilities, it is assumed that the production of a well remains constant during each period, and that its production capacity is restricted by several factors: reservoir dynamics, energy conservation, and matter conservation. Behavior of the pressure at the wellhead with respect to the reservoir. Characteristics of the well pipe, and characteristics of the pipe of the collectors. The central variables of the modeling represent the flow in the wells and the flow in the collectors. This flow may be multi-phase, in the case of crude oil deposits, and single-phase in the case of gas fields. The diagram summarizes the connectivity of the mathematical elements that allow modeling the well, in the aspects related to the pressure and flow of hydrocarbons, along the hydraulic system that is part of the production system. E&P portfolio optimization is based on the capitalization of knowledge, of the interaction between potential projects and existing projects. The aim is to obtain most of the answers required for an optimal decision-making process, so that the decision-makers can answer, among others, the following questions. Is it possible to obtain an expected level of return on investment, without incurring serious cash flow risk? How much can we invest in a new project, given the current structure of the investment portfolio? How do oil-oriented projects affect, in contrast to gas projects, the price risk associated with the investment portfolio? How does global political instability affect the risks associated with the investment portfolio? Analytical models will help directly in the solution of questions like the above, once decision makers become comfortable with the holistic perspective supported by the mathematical quantitative risk analysis. The mathematical models that may be integrated are: optimization of E&P investment portfolio, design of oil production networks, and oil and/or gas production optimization. Smart grids and oil production fields optimization is a new activity of the oil industry. The technical economic viability of energy storage, coupled with the proliferation of renewable energy sources and technologies, has changed the landscape of the industrial sector, since it is now possible, and increasingly efficient, to generate renewable energy and store it for use in due time. In practice, all industrial companies can be agents that interact in the electricity market, since it is possible for all to act as co-generators, and carry out commercial activities and transactions. The industrial energy efficiency strategy implies two stages. Offline optimization, planning, is integrated by 3 steps. Redesign the energy supply system. Optimize the industrial process in the plants using complex mathematical models, and integrate the planning and scheduling of the industrial process, matter transformation, with the industrial services, energy transformation, including the transactions in the energy markets using optimization models. And online optimization, operating, that includes 3 steps. Use an optimization model for pre-dispatch the energy system, 24 hours in advance. Use models oriented to optimum control in real time, dispatch of energy system, and short-time energy trading and risk management. Oil transport, trading and blending optimization corresponds to a dynamic model that optimizes oil distribution between fields, refineries and ports, the oil mix for use in refineries, the mixture of oil for export in accordance with quality standards and established supply contracts, import of oil according to offers in the spot global oil market, and import/export of oil according to offers in the oil derivatives financial instruments. It can be coupled to the production of oil fields, in such a way as to establish optimal plans for production, distribution, export and import. In addition, blending processes extend to petroleum products, for example, lubricants. It can be coupled to the production of oil fields, in such a way as to establish optimal plans for production, distribution, export and import. In addition, blending processes extend to petroleum products, for example, lubricants. Oil refining optimization includes a generic model that can serve interchangeably to plan the crude and/or biomass refining processes that may be spatially detailed in all units used in the production of refined products. Industrial services optimization is the complementary model to the refining model, aimed at optimizing energy management in industrial plants that include large-scale industrial service plants, such as refineries, petrochemicals. These services often include self-generation, cogeneration and the exchange of energy with the interconnected electricity system. The objective of the model is to minimize the consumption, or cost, of the energy required by the industrial processes, supported by the industrial services plants. The industrial services system is coupled with the production process model to holistically optimize the transformation of crude oil into refined products. The simultaneous optimization of both industrial production and energy conversion is related to polluting emissions of gases and liquids, associated with increasingly demanding environmental control laws. HI may integrate complex industrial process models to redesign the power supply system, according to the new power technologies. This type of model includes the simulation of polluting processes to determine the optimal mixture of fuels, in accordance with environmental regulations. Oil transport systems optimization corresponds to a general model, common to all types of oil products, raw, refined, natural gas and biomass, which represents the process for a specific system, including particular equations when this is required. It considers 2 types of transport modes: pipes and multimodal vehicle, like vessels, barges, train tanks, and/or trucks tanks. The integrated transport system can be conceptualized as the junction of pipe and vehicle routes, which interconnect multiple terminals, which are the places where are connected the different installations. Each transport media is modeled independently. System connectivity is done through the terminal, a node, that corresponds to a point in the space in which at least two installations are interconnected, such as oil fields, plantations, oil refineries, biorefineries, port, consumer centers, and thermal plants. HI supports the planning and scheduling of oil products transportation, through pipelines using three coordinated hierarchical models. Tactical planning determines the optimal volumes to be transferred in during the planning period, without considering the sequence of products in the pipelines. Batch scheduling determines the volumes and sequence of tenders to be transferred in during the planning period, considering the volumetric planning established at the previous level. And real-time optimization determines transfer speeds, discharge pressures, and pumping patterns, serial or parallel, at pumping stations, to meet batch scheduling established at the previous level. The optimization goal is to minimize operating costs throughout the entire planning and scheduling process. The real-time models includes non-linear modeling that determine the amount of energy consumed based on the flow of products in the system. In aggregated models, when multiple types of products can be transported in the pipeline, the total transport time must be divided into the time used to transport each type of product at different transfer rates. To represent the flow of energy through the transport system, the following constraints should be considered. Energy conservation in the ducts and nodes of the system. Minimum pressure limits, or compression, at the outlet of the ducts, and pressure, or compression, minimum input to the ducts, depending on the type of connection between the operational area, node, and the duct. In the real-time model, a detailed hydraulic system is available in the pump operation model, for each type of pump in the pumping system, and each link in the pipeline, for each type of product, or crude. This ensures the feasibility of the results. The real-time model can handle differentiated electricity costs by time of day, or by load block, using this way to take advantage of low rates, or low marginal costs, in periods of electricity low load. Similarly, like oil, natural gas supply chain may be modeled as a mathematical model to simulate the transportation and storage of natural gas. The optimization model includes the following types of nodes. Production fields. Consumption center, natural gas demand nodes discriminated by demand sector, among which are industrial, vehicular, electricity generation, commercial, and residential, and ports and terminals that can receive and/or send LNG. It is associated with liquefaction and/or regasification plants. Vessel scheduling optimization supports the programming of collection and/or distribution operations of products via maritime ways, in tankers and barges. It considers restrictions for delivery and load time windows, distribution of capacities on ship, loading and unloading capacity at the docks, draft capacity of the spring, speed of movement of ships, tanker weight to draft ratio, and synchronization of filling, or emptying, of storage tanks. 7th. Planning and scheduling of bulk port terminals. The objective is to minimize the terminal operating cost, considering the system environment, which may include the fuel cost of ships. Managing bulk ports and ships becomes part of the industrial process, since it defines the supply of raw materials and the distribution of finished products that are related to industrial operations. Depending on the specific case, it must be coordinated. The arrivals with consumption in industrial plants, the departures with production in industrial plants, and the storages level with the output of material. The optimization may affect the industrial process's speed and the ship speed. When it is necessary to make decisions about the displacement of the vessel, it is of fundamental importance the correct modeling of the consumption of energy, which has a nonlinear behavior, with respect to the engine speed of the vessel. This constraint can be included in the mathematical model, as well as the modeling of tidal movements when entering or leaving ports. Oil product distribution optimization supports the scheduling of gasoline distribution operations, between terminal products and from product terminals to gas stations. It is applicable to several oil products like gasolines, LNG, LPG and others. The entities of the model are terminals, tanks in the terminals, loading points, service stations, trucks, and drivers. distribution of gasoline and other oil and gas products between terminals, service stations and industrial clients. A mathematical model of distribution of petroleum products or similar should consider the following constraints. Delivery time windows, tank trolley capacity, distribution of tank trolley capacities in multiple compartments, product availability at service stations, product availability at terminals, load capacity of cargo islands, fillers, work shift, and driver assignment. The result is the scheduling of activities by filling pump, filler, tank car, end user and drivers. For a large distributor, the mathematical model may include transport between terminals, and the connection of terminals with other facilities, such as ports and refineries. Maintenance of oil and gas assets optimizes industrial asset maintenance decisions, considering the equipment operating characteristics, and life consumption dimensions prior to next maintenance. It implies the coordination of maintenance resources maximizing its marginal revenue. The idea is to integrate maintenance restrictions into the tactical models. The decisions are the maintenance dates, like months, weeks, days. The objectives functions may be minimize operating plus maintenance costs, or maximize economic benefits. Lifetime consumption before the next maintenance can occur in one, or more, of the following dimensions. Maximum time, days. Time, days, or production, like MWH, BLS, tons, KMTS. Dry docking maintenance scheduling implies the efficient scheduling of ship maintenance that requires dry docking as a vital component in the overall strategic management of a merchant shipping fleet. When this process is managed well, significant revenue and efficiency gains can be made. Like Herbert Simon, Hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.